You know, in math, there are some problems that for centuries, we've just considered impossible. Like real solid walls you just can't get past. But what if one of those walls, one that's been standing for ages, turned out to be, well, not so solid after all?
So what if I told you there's a mathematical rule, one that's been treated as gospel since 1824, a rule that basically says this is as far as you can go? And then, what if someone just strolled right past that line?
Yeah, that's really the heart of what we're talking about today. It's summed up perfectly by this idea that, well, limits are really only limits until somebody breaks them. All right, so to really get why this is such a big deal, we've got to go back. We need to understand the barrier itself. Let's talk about this 200-year-old theorem that basically set the rules for what was possible in algebra.
This is it, the Abel-Ruffini theorem. And you can think of it like a giant cosmic stop sign for mathematicians. It basically said, look, once you get to equations with a power of 5 or higher, that's it. There's no single elegant formula to find the exact answer using the tools we have. It's a dead end, full stop. And think about the implications of that. It meant for 2 centuries, whenever mathematicians faced one of these really complex equations, the best they could ever hope for was just getting close. You know, they could get a numerical approximation, like a super long decimal that gets closer and closer, but a perfect, exact, beautifully simple answer? Nope, that was completely off the table. Impossible.
And this chart right here, it just lays out the battle perfectly. On one side, you got the old guard, the classical method saying, nope, can't be done beyond the 4th degree. But then on the other side, you have this brand new claim from Professor Ezouidi, who says, oh yes, it can. The old way accepts that there are limits. The new way, it completely rejects that idea, calling it mathematical fatalism. I love that phrase. So who's the person brave enough to challenge 200 years of mathematical consensus? Let's dive into this revolutionary new method and the person behind it. Meet Professor Mourad Sultan Ezouidi, and for him, this whole thing wasn't just some abstract puzzle on a blackboard. It was personal. He looked at that 200-year-old wall and didn't see an unbreakable barrier. He saw a line that was just drawn in the wrong place with the wrong tools.
And here's the key thing to understand. His method isn't just a small improvement on the old stuff. It's a whole new way of looking at the problem. He's not trying to brute force his way through the old door. Instead, he's found a completely new key, one that uses things like recursive discriminant relations to just unlock it. He's not breaking the wall. He's showing us there was a hidden door there the whole time.
Okay, so a new theory is cool and all, but does it actually work? Well, this is where things get really, really interesting. Because to prove it, they took on an equation that, for all intents and purposes, should be completely unsolvable.
Just look at this thing. It's a monster, a 20th degree polynomial. I mean, wow. According to that 200-year-old theorem, finding the exact roots for this, absolutely impossible. This isn't just a hill to climb. This is the Mount Everest of unsolvable equations.
And the way he tackles it isn't some kind of magic trick. It's a very clear, logical process. First, he finds a hidden recursive pattern inside the equation. Then, he transforms all the numbers into a new symbolic form. And from there, he can just pull out the exact roots. It's a step-by-step journey, not a leap of faith.
And this is the real game changer. See, you could plug that equation into a supercomputer and it would spit out a long, messy string of decimals. It's an approximation, it's close, but it's not perfect. This method, though, it gives you the pure, clean algebraic answer. The kind of elegant solution that mathematicians dream about. The kind we were told we could never have for this problem. And there it is, the prize, the exact symbolic root. Now look, the formula itself is obviously super complex. We're not going to break it down here. But that's not the point. The point is that it exists. It's a clean, finite expression. It's not a ... that goes on forever. This is the proof. This is the flag planted on top of that mathematical Everest. Okay, so if this holds up, solving one ridiculously hard equation is really just the tip of the iceberg. The implications here are, well, they're huge. This could change everything. Let's talk about what this means for the future. This is really a before and after snapshot of mathematical philosophy. The before view, it sees Abel's theorem as a hard limit, a permanent wall. But the after view, Ezouidi's view, sees it as just a stepping stone, a historical marker that we've now walked past.
It's the difference between saying it's impossible and saying we just hadn't figured it out yet.
And this quote from the paper really nails it. It says, this isn't just about solving one equation. It's about redefining what it even means to solve something. It's changing the rules of the game.
I mean, the potential is just mind-boggling. Think about it. If any polynomial, no matter how ridiculously high its degree, can be solved perfectly, then it's like a whole wing of the mathematics museum that's been locked and dark for 200 years just had all the doors thrown open and the lights switched on. It's a brand new frontier.
So that leaves us with this one big final thought. Because really, this isn't just a story about numbers and equations, is it? It's about how we see the world and its limits. It really makes you wonder, right? How many of the things we think of as impossible in science, in our careers, in our lives, aren't actually walls at all? Maybe they're just waiting for someone, maybe even you, to come along with a new way of looking at them.